Okay, let's look at some examples of how we would use this information. If we look at the first one, we have sodium electrons, and they need a certain amount of energy to be removed from their atoms. That means they're taken from a particular energy level and just ripped right off the atom, or ionizing the sodium. We want to know the frequency of electromagnetic radiation that is necessary to do this. So I have an equation that I need energy and I need frequency. So I'm going to use this equation. And I know the energy, so I have 8.236 times 10 to the negative 19 joules, and that equals Planck's constant, 6.63, times 10 to the negative 34 joule seconds, times the frequency. So this is just basic case of simple algebra, and I get a frequency of 1.31 times 10 to the 15 hertz. The next one we're going to look at is we have an electron that has to absorb 3 electron volts, so we're changing our energy units here, and it wants to jump from n equals 1 to n equals 2, and I need a wavelength of light. So first thing I want to do is I want to get electron volts to joules. So now I've got my energy in joules, and I'm going to use the energy to wavelength, so we have hc over lambda. C, remember, is the speed of electromagnetic radiation. So this is the change in energy for the electrons to go from one energy level to the next energy level. So now I just have to fill in Planck's constant and C because I know those values. Planck's constant, again, 6.63 times 10 to the negative 34. C is the speed of electromagnetic radiation, 3.0 times 10 to the 8th meters per second. I do the math, punch it all in my calculator, and what I should end up with is 4.14 times 10 to the negative 7 meters, and that's 414 nanometers. Wavelengths of light actually are usually given in nanometers, which is why I gave you it that way. Here's a third example. We have an electron in the ground state, and they give us the energy of the electron in that state. It's negative 10 eV, and it absorbs a photon with an energy of 11 eV. So the photon coming in has more energy than the electron in its ground state, and that allows the electron to be knocked out of the atom, and we want to find out what speed the electron has when it leaves. Well, the energy is going to be transferred from the photon to the electron, and energy left over is going to be energy that is kinetic energy of the electron as it leaves the atom. So first thing we need to do is figure out how much energy is left over, which is a fairly straightforward algebra. So we have 1 eV of energy left over. So as the electron leaves the atom, it's got 1 eV of energy. If I want to figure out how fast it's going, I have to convert that eV of energy into joules of energy. So 1 eV is equal to 1.6 times 10 to the negative 19 joules. That's equal to the kinetic energy of the electron, so 1/2 times the mass times the velocity squared of our electron. So we have 1.6 times 10 to the negative 19 joules equals 1/2 times the mass of an electron, 9.11 times 10 to the negative 31 kilograms, v squared. And we find a velocity of our electron of 5.93 times 10 to the 5th meters per second. Our next problem, we're going to take a look at infrared light. It has a wavelength given to us, 1.284 times 10 to the 6 meters, and that wavelength of light is created when electrons of a hydrogen atom fall, and they start at n equals 5, and we're supposed to figure out at what energy level they land. So the first thing I have to do is take that wavelength and convert it into energy. So energy equals hc over lambda. H is 6.63 times 10 to the negative 34. C is 3.0 times 10 to the 8th meters per second. And that's all over my wavelength, 1.284 times 10 to the 6th meters, negative 6 meters. It's a small wave. And we can figure out the energy from that, plugging in all of our values. We get 1.55 times 10 to the negative 19 joules. Now, remember we said if energy is positive, we have to make that 2.178 value positive also. So we're going to remember to do that. And this is our change in energy for the electron. So 1.55 times 10 to the negative 19 joules equals 2.178 times 10 to the negative 18 joules times 1 over our final energy level squared minus 1 over our initial energy level, which is n equals 5, so 5 squared. So first thing I'm going to do is divide both sides by 2.178 times 10 to the negative 18 joules, and I get 0.07117. And that equals 1 over my final energy level squared minus 1 over 25. So now I'm going to add 1 over 25 to both sides. I get 0.111 repeating, almost. Make this a 2 if we round it. And that equals 1 over NF squared. Take the inverse of both sides. I get 8.995, which is about 9 equals N squared. So N equals 3. So in this problem, my electron started at N equals 5. It gave off a particular wavelength of light when it fell to N equals 3. And so that walks us through the last of our problems for chapter 23.